Welcome to the NASA series Exploring the Moon, where we take a behind-the-scenes look at the preparations for humanity's return to the Moon.
The lighting conditions are going to be very different between Apollo and Artemis. We're taking the ability to transport crew and tools and these Mars rovers that can operate independent of the crew, and we're putting them together.
The South Pole is really hard to drive in.
It's going to be quite an adventure and be able to get some good science out of it.
That is the whole reason we're going. We're going for the science.
I think it's pretty cool.
Hi, I'm Stephanie Cipolla, and in this episode, we are honored to have Nathan Howard, who is an expert on moon rovers. Hi, Nathan. It's good to have you here today.
Hi, Stephanie. It's really good to be here.
So, Nathan, I wanted to start our discussion today with the idea of humans returning to the moon as part of the Artemis campaign. We have these rovers that we designed for Apollo. They were single-use rovers. They're still sitting on the surface of the moon. Tell me, what's going to be the difference between the Apollo rovers and the new rovers that we need for Artemis?
Okay, so the Apollo rovers, as I said, they were single-use vehicles. And so they were designed for one purpose, and that was to carry the crew and the equipment they needed during the mission, and then they were done. For the Artemis campaign, we are going to learn how to live on Mars in the future. And so we're designing a vehicle that can last longer. And so if you want to compare the Apollo rover to, say, the amazing Mars rovers that are out there, we're taking the ability to transport crew and tools and these Mars rovers that can operate independent of the crew, and we're putting them together. The lighting conditions are going to be very different between Apollo and Artemis. During Apollo, because they landed equatorial, they wanted to land either in the morning or in the afternoon. And the reason for that is in the morning, you're able to get shadows and you're able to give yourself some depth perception or depth cues. If you were to land during the middle of the day, you get very harsh light straight overhead, and it's very difficult. We're going to run into a different problem on the South Pole. At the South Pole, the sun never gets more than a few degrees off the horizon, which creates very difficult lighting conditions from the standpoint of sometimes you're going to be driving directly into the sun, and it's going to make it hard to see what's going on. The other part of that is it creates long shadows. And so you could end up being in the shadow from a mountain that is kilometers away because the sun is at such a low angle. It's casting these long shadows. It's like taking a flashlight and holding it real close to a table and seeing how long the shadows can make from just little bitty things.
It sounds like you're describing driving at sunrise or driving at sunset, perhaps directly into the sun.
Oh, yes. There's, for those of us in Houston, there are certain times of the year where I'm coming into work or I'm leaving work and the sun is right on the horizon, and it makes it very difficult.
Makes you wonder if the rover is going to have some sort of special windshield to protect from the low sun angle.
That's one of the things that will be part of the design challenges. What are we going to have within the system, and the system being both the rovers and the landers and the suits to help the astronauts perform the best? The suits might even have sunshades. I know they have sunshades for ISS operations.
It becomes an integrated problem to solve. You have lots of tools that you can aid the astronauts with. You have lots of tools you can give to the astronauts to make their job a little bit easier.
That's true. That's true.
So I have this great video here of what the sun conditions look like at the South Pole. Can you explain to us what we're looking at?
The moon is traveling around the Earth, but we always see the same face, which means that the sun is always coming across the moon at different angles as the moon orbits the Earth. And so what we're looking at here is how those shadows change over the course of days and a year. And what you'll see is that kind of in the middle of the screen, there's a crater, and that's where the South Pole is. And then you'll see these shadows that pass across. And some of those shadows are from a mountain, Malpert Massive, that is more than 100 kilometers away. But that shadow, because the sun is such at a low angle, is actually still putting the area in darkness.
Nice, thank you. I have a really great image coming up next that shows the same craters and the same part of the lunar South Pole. The star in the middle, I believe, is the actual South Pole marker. And then the graphic also has red areas and blue areas. What do those indicate for us?
So, Stephanie, you're right. The star marks where the South Pole is. And you'll see that the South Pole is actually right on the rim of what's called Shackleton Crater.
Mm-hmm.
The red areas represent the highest elevation. And so if you think about it, red is high and then blue is low. And so in the upper right-hand corner, you see Shoemaker Crater.
Mm-hmm.
That one is the lowest area in this image because it's deep. And so those areas stay dark for a very long period of time.
Okay.
The high areas, they get the most sun. And what scientists have found is that the connecting ridge, which is actually just a local high area between Shackleton Crater and Degrelach Crater, is an area of the moon that receives light most of the year.
So let's turn all of this lunar environment knowledge into a rover. How does the light environment and the sun environment you're describing, how does that affect the design and the capabilities needed from a rover?
So the rover is going to have to be able to survive both light and dark conditions and take advantage of the light when it has it and be able to survive the dark. And so we have found that there's areas of the moon that stay lit most of the time around the South Pole. Once you get away from the South Pole, most of the moon has 14 days of light and 14 days of dark. So if you're going to operate in the South Pole, you need to figure out how much dark do you have to survive. And so we figured out that there are areas in the moon where we can minimize that period of darkness. And so the idea would be to stay in the sun as long as you can, charge up your batteries, and then go to those locations that stay light most of the time. And whenever a shadow does come, you do like a bear. You go and hibernate, go to sleep for a little bit, and then when the sun comes back out, you wake back up and you continue exploring.
It's a combination of planning your day and planning your excursions on top of designing a vehicle to handle these lighting conditions.
That is absolutely right. You have to think about it as an integrated problem, both the vehicle design and the mission design. Because some of the things that we want to be able to do is we want to be able to travel between these, call them hibernation points. We want to be able to travel between these points because there may be additional science we want to explore. And traveling between those points is going to take a lot of planning and vehicle design.
You shared with us another graphic that I'd like to pull up right now. And in this video, we can see two dots moving across red lines. The image on the right, I clearly understand, that is us floating above the surface of the moon looking down, and the red track is the track that the rover takes, and the green dot is the rover. Help me understand what's happening in the left graphic.
So you're absolutely right. The green dot is the rover as it travels along the red path. And so what we're looking at here is how would the rover travel between some of these high points and stay in the sun? And so, well, in this case, think about the shadows, the big black bars on here as the shadows. And those shadows, if you get stuck in those are probably going to be long enough that your vehicle can't survive. So you have to plan out when you're going to go forward, when you're going to stop, and when you're going to go forward again. And so if you notice between the two graphics, there are periods of time where the rover looks like it could drive forward and keep going, but it's sitting there stopped, and you wonder why. Well, the reason is that you don't have enough time to get to the next stop point before a shadow comes. And so you actually have to stop and wait for the shadows to move around you before you can move on to the next point.
This is really complicated. I always assumed building a rover for the moon would be pretty easy.
Well, that's kind of interesting, because during the Apollo era, they thought the exact same thing. They thought, okay, it's a simple rover. We'll go put it on the moon. Well, once they got into it, they realized that they had a lot of mass constraints. They knew that they had mass constraints. They had volume constraints. They had complexity that was just phenomenal. And we are understanding the same thing as well, is that the rover is a very complex piece of a very complex system. Not only is it, how do you get from one point to the other? How are you able to support the science? How are you able to do simple things like phone home? Because just getting communication there is more difficult. During Apollo, it was a lot easier because they were equatorial. The moon's tidal locked. If they wanted to know where the Earth was, all they had to do was look up. It was always right there in the sky. Because we're at the South Pole, we have to pay attention to where is the Earth relative to where we're at. And because the terrain is referred to, as highland type terrain, we could very easily dip below a hill and not be able to see Earth.
How do we train ourselves and our astronauts to drive in these difficult conditions?
We can train the astronauts using simulators, and we have used data collected from the Lunar Reconnaissance Orbiter and its instruments to create topographic maps. And then we take those topographic maps and we put them in a simulation environment. And some folks might be interested to know that it's the same sort of simulation environment that they use to create a lot of the video games. They put the terrain in there, they put the rover in there, you put the sun in there, and then you get the same lighting conditions that you would expect at the South Pole. So you're able to train the astronauts in an environment that they would expect when they get there. Stephanie, the other day I had the opportunity to show astronaut Tracy Dyson how to drive a moon rover in one of our simulations.
I'd love to see that video.
Well, welcome to the Systems Engineering Simulator, a simulation of the lunar South Pole environment.
I'm excited about this.
Some of the fun things that you're gonna find out is that the South Pole is really hard to drive in because of the lighting.
Okay.
So to get started, what you would do is you'd release the parking brake.
Okay.
Okay, so let's on that. And there you go. You see the wheel.
I do. I see the wheels are ready.
A little bit.
All right.
Okay. And so if you want to drive forward, you just push forward.
What's top speed on this guy?
It's 15 kilometers per hour.
Oh.
And so one of the things that's interesting about the South Pole is because the sun is so low,
Yeah.
you see all these craters and these rocks. The craters don't get much sun down in them, and so you can't tell how deep they are
Oh,
or how
wow.
big they are. So you're going to want to try to avoid some of those. The rocks, you can see that they're kind of small, but they're casting these long shadows. And that's one of the things about the South Pole that's going to be fun to navigate. And so you push forward.
Okay.
So don't worry, we can reset the simulation if you get stuck on anything. And there you go.
Right. Handle that little rock there.
Around. And you can see all the different craters that we're expecting. And that right now we're up on Connecting Ridge.
That's the name of it?
Connecting Ridge is what everybody calls it, and it actually connects Shackleton Crater to Degralash Crater. So it's a local high area right on the South Pole.
So now, if I try to go between these craters,
Well, go ahead and drive.
I'm going to do
through
it.
And you start to see here that this one might be a little deeper. Go ahead and drive through, and the vehicle will react, leaning over to one side
yes?
as you drop down in the crater.
All right. I'm going to open it up a little bit.
Yeah, open it up.
I feel like I'm.
And that's one of the reasons why we're doing this, is so that the astronauts, when they're getting ready to go to the South Pole, they can get an idea of what it's like to drive before they actually get there. And
Yeah.
then you can see all these little rocks, they popped into view as you got closer as well.
Yeah. Oh, I see what you're saying. Those little
The little rocks.
little guys.
And they can tell you where, where the sun is coming, give you an idea of where the sun's coming from.
Now, this is in reality going to be all open, right? So I'll have windows all around me, basically, or I'll be able to see.
This is the unpressurized rover. So this is very similar to the Lunar Roving Vehicle from Apollo.
Oh,
So you'll be in your suit
I got you.
and able to, your view will be as big as your helmet. So now you can see starting to go downhill, and you've got an inclinometer there on your display,
Oh, I
a
do.
little bubble right here. So you
Okay.
can see you're kind of tipped over to the right a little bit. And then if you point it more downhill, you'll see the bubble move around. So it's downhill, open, go ahead, open it
All
up.
right, we're going.
If you turn to your right and start looking towards the sun, you'll see what it's like driving
Wait, toward the sun, you said?
towards the sun. Yeah,
Okay.
if you turn, you'll see how difficult it might be to start driving facing the sun. See there, you can see that crater, but you
Oh, man.
you don't really,
You
can't
don't know
really-
what's on the other side.
No, you don't. You don't know at all. Here you can see headed back towards the Hab. And
So
you
that,
had driven off over this way, and now you're coming back around. So this was the local low area that you drove around.
wow. I'm just in awe at the moment.
So the goal here is to work with the data that we've been able to collect from the Lunar Reconnaissance Orbiter with all the elevation maps and everything,
Yeah.
create the topography, and then come in, and then the planetary scientists come in and tell us, should these be big rocks, little rocks? How big are the the craters? So like if you try to drive over that rock,
I'm trying
are you going
right
to
now.
go over it? And then do you get stuck?
Oh, I got stuck. So
There's-
I'm going to break an axle on me.
No, you're not going to break an axle in the sim.
So what if this happened to me in real life? What would I do?
Well,
Do we have like a,
yeah, that in the Apollo era, they actually could just pick up the vehicle and move it.
oh, they just get up and
They
get
could just
out?
pick up and move it. This vehicle is going to be different. It's going to have a lot more capability.
Just did it. Well, I
There
didn't do
you
it.
go.
I did it. All right. We got out everything.
There you go. Now you can see your tracks.
Oh, this is so cool.
Okay. So as you can see, if you look right here in this area, you can see a depression area right there. And so you can go and you could try to drive down
No
through
kidding.
there.
All right. Going into the crater.
Yeah, but see, you can't
Oh,
see what's down
No,
in
I don't
there.
want to go there. I'll get stuck, huh?
You
You can
might
pull
get-
me out, right?
You might get, yeah, we can get you out.
Oh,
Go
God.
explore down in there and see what it's like when it gets dark.
It's crazy. It looks like a really steep wall on the other side.
It does.
Don't try this at home. All right. I'm going in. Oh, look at that.
So there you go. You can see now you're tipping off to the side.
Yeah. I feel like I'm
Yeah.
in a dune
There you
buggy.
go. There you go.
Yeah. Look at that.
So there you go. In and out.
We did it. We did it. You probably had no doubt. You're like, this vehicle can handle it.
That's right. That's right.
Oh my. So that's a shadow then?
That's a shadow of a mountain that's behind you.
Oh wow.
So that's one of the things about about the South Pole is even though it's illuminated most of the time,
It's got some wicked
it's got
shadows.
some wicked shadows. So like right here, you have no idea what's down in there. So
Almost like driving in fog, where
yeah, you can't see
you can't see in front of you, except like 2 feet. You're already on top of it. Wow.
Okay, so now you're seeing where the sun is just barely clipping the top of the.
Is that
Top
the
of the
mountain that was behind me, or the mountain that I was headed for?
That's the mountain you were headed for right there. So you're down in the shadow,
Oh,
and you can see where the light was coming through, and it's cast this long shadow. So if you continue up that,
Oh,
you'll get up out of the. You'll eventually come up out of the shadow.
oh wow. I bet it's pretty cold down here too. Huh?
That's right. So the other thing about the South Pole is it's got these cold traps in it
Mhm.
that or part of the reason we're going there, because we're looking at the possibility of having water
Yes.
trapped in those areas. Okay, so it looks like you're getting pretty close to the edge of the shadow now.
Okay. Should we like slow down and make it dramatic?
There you go.
Yeah.
So you can see how sharp that shadow line is, because you don't get any of the light scatter that you get from the atmosphere here. There you go. All of a sudden,
Wow. And there you are.
back in the light.
Oh my gosh. That was
Right.
super crazy.
There you go.
Let me
So
look at that.
that's what you were.
And so I started on the other side
You
of that
started
shadow.
on the other side of that shadow. You went all the way down through there and came right back out. So now that you've had a chance to drive the simulator, what are your thoughts?
My thoughts are that this takes some practice, but it reminds me a lot of riding motorcycles out in the deserts of Southern California, where you have flat terrain, but all these features, and there's potholes that could come up, and you have to think quick before you react to them, before you can get out of the way. But I also think that it's fascinating just the fact you're on the moon's surface, and how you were describing the sun and the shadows on the terrain, and how they change, and how shadows are, they appear to be like these sheer drop-offs, but
Right.
they're actually, some of them are just inclines, and our job is going to be to go explore these areas.
Absolutely.
So it's, I think, just having first of all, this vision to go and do this is pretty exciting. The fact that we can take all of the data that we had from our Apollo days and put it to use like this is also pretty exciting.
Absolutely.
I think
Absolutely.
This is going to be a fun tool.
It's absolutely going to be fun, and it's hopefully going to make all your lives easier in the years to come.
I was going to say that any little bit helps, because this is going to be quite an adventure to go for the long haul and sustain presence there and be able to get some good science out of it.
Yep. That is the whole reason we're going. We're going for the science.
I think it's pretty cool, and I appreciate it.
No problem. We're happy to have you.
Awesome.
Welcome back anytime.
Thank you.
So just like driving around your neighborhood, you drive it enough times, you know where everything is.
I bet that makes everybody feel a lot more comfortable.
I know it would make me feel comfortable.
And what about the simulators? Do we use them for anything besides astronaut training?
Yes, we use the simulators for other things as well. We can use them to help plan out science missions, as well as train the astronauts.
Nathan, how do the science requirements for the Artemis campaign influence the rover design?
Science has influenced the design of the lunar rover. We are designing it in such a way that it can accommodate different payloads across its mission, where we could change out what we want to carry from one mission to the next.
How many lunar terrain vehicles will there be in the Artemis campaign?
Well, right now, we don't know how many rovers there will be. We are asking industry to go out and help us understand what's the most efficient way to explore the moon for 10 years. It's not just how much does something cost, but also from the standpoint of how much crew time would it take to maintain a vehicle over 10 years.
The rover that you shared with NASA astronaut Tracy Dyson earlier this week, what is it used for? Why does NASA have it?
Yes, we are putting together a reference design, and we are also in the process of building a ground test unit. We call it the GTU. And so the reference design is what Tracy was able to drive in the simulator. And so that's a design that really helps us understand operations in the lunar environment, looking at the lighting, looking at just getting from point A to point B. And there's things that we have learned over the last 1.5 to 2 years that we didn't even know we didn't know when we started this. The ground test unit is kind of the other side of the coin, where we need something that our astronauts and our trainers and our engineers can interact with physically to understand, how do you physically interact with this thing? What do we need its capabilities to be? How are we going to use it within the larger architecture, not just on paper, but how are we actually physically going to interact with this thing? So we're putting that together, and then we're planning to use it to help us better understand the vendor designs when those come out.
Has the rover ground test unit been tested in different analog conditions?
Not yet. The ground test unit we are still in the process of developing it.
Will the ground test unit allow us to practice changing wheels and other types of rover maintenance that we might need?
Yes, the ground test unit could be used for a variety of different use cases. So one of the things could be, how do you perform maintenance on the vehicle? We know that across 10 years, the vehicle is going to need maintenance. And so even though we don't know the design of the final vehicle yet, we do know that there are likely things that we will have to do. And so we can look at changing a wheel. We could look at changing other pieces of equipment. The other thing that we can look at is simple things like, where do you put the steering wheel? Do we even have a steering wheel? Do we have computer screens? What else do we have? So we can use this to help us better understand how we could use the vehicle and how we would interact with it in the future.
Nathan, thank you so much for joining us today and sharing with us an inside look of the Moon Rovers.
Thank you, Stephanie. It has been a pleasure to be here.